So thank you very much. It's a pleasure to be here. I want to thank the organizers for inviting me to speak. And just like Jennifer's keynote this morning, I'm happy if this is an interactive presentation. I won't have complicated puzzles for you to solve. But if you have questions, feel free to just raise your hand and ask me questions as we go along. So I thought I would talk about something that's been on my mind for a while, which is a sudden resurgence of interest over the last few years in compiler research. So compilers are one of the oldest and perhaps stodgiest areas in computer science, but it has really seen a resurgence of interest in the last, say 5-6 years. And I thought about having a slightly different title. I actually wanted to name this Trends in Translator Research, but nobody talks about translators. They talk about compilers, and so I left it the way it was. But really, I mean something slightly more different, more general than compilers, and I'll get to that during the talk. So who am I? Well, as the kind introduction just said, I'm a professor of computer science. And I'm interested primarily in programming languages and compilers. I've worked in both academia and in industry research. But for the purpose of this talk, I will talk a little bit about some research efforts at Stanford towards the end of the talk. But mostly what I want to get across is some things that I've noticed as an observer. And so I'll talk about what I've seen and where things have been going over not just the last 5 or 6 years, but over the last 25 years. All right, but before I can do that, I have to tell you a little bit about my point of view and define what I mean by a programming language and a compiler. So what's a programming language? Okay, this is a really easy one. It's a language for writing programs. Okay, it doesn't. It's a well-named thing. It means exactly what it says. Now, but what is a compiler? Okay, and so this is actually not a very good name. It doesn't immediately convey what it does, and I think from my point of view, it's a translator. Okay, so it's something that's going to take a program written in some language and it's going to translate it usually to another language. Okay, so it's really a language-to-language translation, and that translation has to have certain properties. The most important one is that it preserves semantics. So there's some idea of what the program is supposed to do, and the translator actually conserves that meaning when it performs the translation. There are a couple other properties that are very important. Usually we're interested in performance, and so we want the translator to produce a translation that performs well on the target implementation. And we also might care about how easy the language is to use, either for a human or for another machine that's generating these programs. All right, so there's a usability aspect, there's a performance aspect, but there's also a correctness aspect in these translations. And compilers are just one kind of translator. So when people think of a compiler, they think of a static, offline program that is taking programs in some written form, usually in a file, and translating them, say, to machine code or something like that. But it's a process that's done offline before you actually run the program. And then interpreters would be a different style of implementation, a different kind of translator. A just-in-time compiler would be yet a different kind of translator. But these are all language implementations. They're all translators. Okay, and so the talk really is about this whole class of technologies for implementing programming languages of various kinds and at all different levels of abstraction. Okay, so from very low-level languages all the way up to very high-level languages. So to just understand, or just to review, I'm sure everybody here is familiar with programs, and many people have probably had a compiler class. Actually, this would be a good question. How many people have had at least some exposure to compilers in a course at some point in time? So please raise your hand. Yeah, so most people have seen this, what a compiler is or what a language implementation, how that works. All right, but it's worth talking about a little bit just how deeply embedded this is in the way the technology industry, the software industry works. So let's take a language like Java. How is Java actually implemented? Okay, this is a language that's used by millions of programmers. There's lots and lots of code written in Java. It's just one of many popular general purpose languages. Okay, so typically, the first step in implementing Java is that there is a compiler, okay, a full software compiler that does all the usual things a compiler does, that translates Java down to Java bytecode. Okay, so that is the first step. But then Java bytecode, what's that? That's just another language. Okay, it's nothing special. It doesn't run by itself. how is Java bytecode implemented? Well, it turns out there's another compiler, okay? So these days, very frequently, there will be a translation from bytecode down to LLVM, okay? Because LLVM has become the least common denominator in many back-end implementations, okay? So you'll have a translator from Java bytecode down to, say, LLVM, all right? And LLVM stands for low-level virtual machine. If you haven't heard about it, it's just a high-level assembly language, okay? That's all it is, and very portable. All right, well, so then how is LLVM implemented? Well, again, it's just another language, okay? It doesn't run by itself. You know, there must be some other way of implementing it. It's done by yet another translator. All right, and what's that one look like? Well, LLVM has a whole bunch of translators inside of it that target various specific machines. So there'll be one, for example, to translate to x86 assembly language. Okay, so you take the general purpose portable assembly language and you translate it to the very specific hardware, you know, machine dependent or machine specific assembly language for the x86 architecture. All right, well then how is x86 implemented? It's just another language. I mean, it's just a text file with a bunch of stuff in it, and there must be another implementation. And so in fact, there's something called an assembler that actually translates it into machine code. All right? And then how is machine code implemented? And people might believe that machine code just runs on the bare hardware, but that actually isn't true. So when you run machine code on the hardware, inside the hardware is another on-the-fly translation that translates the machine instructions down to even more primitive microcode that's not exposed to the programmers. And the microcode actually runs directly on the machine. Okay, so the microcode is actually the primitive level building blocks that you never see inside the modern architectures. And so just to implement one programming language like Java, you have all these levels of translation. And most of our software, okay, most of the software that we use and that we write goes through many, many, many levels of translation to actually get down to something that runs. Okay? And this has been built up over decades. All right, so this technology and this infrastructure has accreted and accumulated, and there are stacks that are much deeper than this, okay, for some programming language implementations. All right, so what I'm going to talk about in this talk is all those different kinds of translators and the general technology forces that are causing us to reconsider, or will cause us to reconsider a lot of those stacks of translation. And I'll talk a little bit about some history, okay, and then I'll talk about what's happening now. So here's a picture that we're going to see again. Some of you may have seen a picture of like this in the past. This is an architecture picture now of the trends in Intel processors since 1970. And there are various lines on this graph. I will talk about all but one of them. So we don't need to go into detail now. I'll come back to each one of them. But you can see that all of these lines over the history of the last 40 years have been basically up and to the right. So things have been getting faster and better over time. All right, but let's start by just focusing on one period of time. The period between about 1990 and the early 2000s, up to about 2004, 2005, something like that. Okay, so I'm just going to, let's rewind to 1990 for those of us who actually remember that year, who were actually alive then. And let's say that I was a programmer in 1990, and I wanted my program to run faster. All right, so my boss told me, this program has to run twice as fast, or whatever, the driving force was that caused this, to need to be done. And what were my options? Okay, what could I do in 1990 to make my program run faster? Well, one option is to work hard. Okay, so I could just get in there and start working on the program, and if I understood how machines worked and a lot of different kinds of tricks, I could very likely, with enough effort, make the program run faster. Another option is to invest in better tools. I could say, well, instead of making the program run faster, I'm going to go and work on the compiler. I'm going to make the compiler better, and then when the compiler is better and generates better code, that'll make my program run faster. Not only will it make my program run faster, you'll make lots of other programs run faster. Okay, so if I thought there was some place where the compiler could be improved, that might be the best way to invest in improving the speed of even this particular program. Or I could wait 18 months and buy a new computer. Okay, and my question for you, actually I apologize, I lied to you. I have one question for you, and I'll wait for the answer. What do you think people did? Wait 18 months. It's by far the easiest solution, right? And so that's what they did. And so because machines were getting better, you didn't have to actually work very hard to make your software run faster. You just had to wait until the next generation of technology came out. And if we go back to the graph, take a look at the scale. Okay, this is a log scale, all right? So, or an exponential scale. So, you know, every tick up there is 10 times better. So these are very rapid improvements. And essentially in that window of time, every 18 months, the processors got to be twice as fast. And you wouldn't quite realize all of that improvement for various reasons, but you would notice, even over that short period of time, even if you did nothing else you did nothing to your program, that it got faster, substantially faster in a year and a half between, you know, just one generation of machines. All right. Yes, the log scale. Okay. So this was called the free lunch. All right. And so with absolutely no work, programs kept getting faster. And on the positive side, which is an extremely positive thing for society and the world, this was a huge force for innovation, because you had all kinds of application domains that were just out of reach and then would open up entirely new industries when suddenly they became within reach. So, you know, we don't even remember when computer graphics, you know, suddenly became an industry, and computer games and all those things were enabled by, you know, at some point by this transition, and the ability to have phone calls, the ability to process large data sets, so lots and lots of things, the ability to, you know, have efficient computations over the web, all of these things, you know, were enabled at some point. At some point they were impossible in pipe dreams, and then suddenly, with the improvements in processing power, they suddenly became possible, and in many cases, you know, started very large companies and industries, and, you know, changed the way people work in the world. All right. But the downside, at least for somebody who's interested in programming languages and compilers, was that there was absolutely no incentive to invest in making the programming languages and compilers better during this period of time. And in fact, its story is slightly worse than that. There were negative incentives, okay? Because the sad reality is that generally new new software tools take about a decade to mature. So from the inception until the stuff actually really works and people can use it easily, you know, it takes many years to develop a complex system like a full language implementation. And what immaturity of one of those systems means, almost by definition, is that it doesn't run very well on the latest hardware. And so if you were somebody who was interested in trying out new language technology in the 1990s, you were generally not able to run on the newest generation of processors, and that meant you weren't taking advantage of the improvements that were coming all the time. And so not rocking the boat, not actually moving to immature compilers and language implementations was a safer way to get performance improvement than to try experimentation. Okay, so during this period of time, there was very little innovation in much of the language design and implementation world. All right, now let's talk about what's happened in more recent times. And this graph, unfortunately, this is an old picture. So it ends around 2007, 2008, but nothing has really changed since then. Okay, so all the trends that are immediately visible there at the right end of the graph have pretty much continued. So the lines that are flat have stayed flat, and the line that was going up has continued to go up. All right. Okay, so in 2010, so just a few years ago, if I want my program to run faster, what can I do? Okay, well, I could do nothing. Okay, just like I did in 1990. Okay, if you know, maybe that would still work. I could work hard, all right, or I could invest in better tools. Same three options I had before, all right. And so now, what works given the current technology trends? So, well, if I decide to do nothing, this particular line is clock rate. This is clock frequency. Okay, so this is how many instructions per second, you know, a processor can execute. And the exact number doesn't matter. The point being, though, that it doesn't get better when the line is flat. That means from year to year, you can execute the same number of instructions per second on a single CPU or core that you could the previous year. Okay, well, so if I do nothing, in fact, what happens today is that my program will run the same speed on a new computer that it ran on the previous computer. Okay, so just waiting doesn't work anymore. And in fact, if anything, my program might run a little bit slower. All right, and because for various technical reasons, the chip producers have been actually decreasing the clock frequency slightly in recent years. Okay, so that line is either flat or drifting down very slightly. Okay, over the last decade. All right, so doing nothing is no longer an option. Okay, so now you actually have to do something. So you have two other options. Well, one was to work hard. Okay, so what happens if you want to work hard? Well, there's two issues here. One is that, again, what's improving? Where are the opportunities for actually making your program run faster? And the only thing that's going up now is the number of transistors. And this is a common misconception. So I think many people are aware that machines haven't been getting faster over the last 10 years, but that doesn't mean that they haven't been able to put more transistors on a chip. They're still able to pack, that has been continuing at about the same rate it always has been over the last decade. So every 18 months or so, you can still get twice as many transistors on the chip as you could, for the previous generation of chips. All right, now that may be coming to an end actually in the next few years. But people have predicted this so many times that you want to wait to actually see the curve flatten out before saying it has really stopped. So anyway, while clock frequency has not been increasing, the number of transistors in the same space has still been doubling at a regular rate for the last decade and for the 40, 50 years before that. But how do you take advantage of all those transistors? Well, basically what that means is you have to parallelize your program. If individual components don't run any faster, if you can't get like a single CPU to push more instructions through at a faster rate, then the only way to get more performance is to take advantage of the fact that you can put many more CPUs on a chip than you used to be able to. All right, so now the way to speed things up is to write a parallel program rather than a sequential program. Okay. And what that translates, I'm not going to go into all the vagaries of writing parallel programs in this talk, but what that really means, bottom line, is that you have to work a lot harder. Okay, so it's not just a small step in programming effort to get a big performance improvement these days. You need to really know how to take advantage of the parallelism that's in the hardware and write a parallel program, which is much, much bigger challenge than writing a sequential program. And you're limited by scarce expertise. If you're a corporation or a manager of a group or something like that, the number of people you can find who actually know how to do this is very, in very short supply. So if you think programming talent is limited just for writing ordinary programs, it's even more limited for writing parallel programs. Okay, so there's only so much you can really get here. All right, so what's left? So if you're limited in the ability to write parallel programs and to take advantage of the hardware, well, then the only thing that's left is to invest in better tools. Okay, and so I think the reason for the resurgence in interest is not so much because people are inherently interested in compilers and programming languages, it's because it's actually the best option right now. It's the highest leverage option for making general improvements in the performance and quality of the software that you have. Because the hardware by itself is not getting any faster. You have very few programmers who can actually manage the complexity of the hardware. So what you really need is better tools. Okay, you don't need very many people to do that, to write better tools, to then take advantage of the hardware and provide programmers with a reasonable interface that you can actually train people to understand and to produce software for. All right, so there's been a migration back, and actually it's been driven primarily by the industry. So the industry is desperate for people who actually know how to write these tools. Okay, and there's a huge demand for not enough students being produced actually, who actually know how to do this sort of thing, how to build translators of all kinds for what's becoming the current generation and future generations of hardware. All right, now. So let's talk about that hardware a little bit. So I showed you the graphs, but what actually does this hardware look like? Well, at the high end, you have supercomputers, and this is a picture of the big one in the United States, the Titan supercomputer, and here's the one in China. So these are the top two machines in the world. But then you also have your laptop, okay? And pretty much inside your laptop, there's a huge number of processors, there's a whole distributed communication network, there's a very complicated memory hierarchy, all right? So the only difference in programming the laptop versus the gigantic machine is both the number of processors and the fact that you don't have a wide area kind of interconnect. So you don't have fiber running inside your laptop, you have something else. But it's really a difference in the network. Everything else in your laptop is present in those supercomputers with the same kinds of complications. And even on the phone. All right, so this phone probably has a dozen processors in it at least, okay? And they're very, very different from each other. There's GPUs, there's CPUs, there's various other kinds of specialized processors to do signal processing and things like that. It's a very complicated setup for how even the phone is organized. And will only get more complex in the future. So what are the properties essentially at all scales of current hardware? One is heterogeneity. So you don't have just one kind of processor, and you don't just have one processor. You have multiple processors and multiple kinds of processors. So the CPUs are programmed very differently, for example, from the GPUs. You have a distributed memory. All of these machines have a non-uniform distributed memory. So you have very, very large fast memories, you have very small slow memories, and very irregular often. So the GPU has its own kind of memory with special characteristics. The CPUs have different kinds of memory. Some parts of the system have cache, some do not. Programming this stuff and getting any kind of performance out of it is actually very complicated. And then finally, there's many disparities that are, in the rates at which things can be done at all. Again, and this applies at all scales, from the supercomputers down to the phone. So the amount you can compute, the number of operations you can do per second, which is usually characterized by flops, is growing much, much faster than you can move data around. All right, so you can move data. You can always do more computation. Every year you can do way more computation than you could before. Every year you can move data faster than you could before, but the rate at which you can move the data is not growing as fast as the rate at which you can do computation. And similarly, the latency, so how long it takes from when you start sending data to when it begins to arrive, that is not improving as fast as the bandwidth, as the amount of data that you can move over a given unit, So the amount of data you can move per second is improving faster than the latency. So the time from when you start moving data to when it begins to arrive is improving. All right. So, and why is that? Okay, so why are there these discrepancies? Why are these machines, why are the architectures so complicated? They're much more complicated than they were even 5 or 6 years ago. Well, that's another line in this graph, okay? And that's the power line. All right, and this is the thing that's actually driving most of the changes. So we've reached a point where the ability to essentially dissipate heat in these machines has reached a limit. So in a given space, in a chip, you can only generate so much heat before the chip will melt. All right, and we've reached that. And the ability to cool that is limited by the fact that everybody wants to use air cooling because it's much cheaper than building some kind of liquid cooling. All right, so you have a power budget. You have a limited amount of power per square inch of CPU real estate that you can actually supply. And if you exceed that, your chip will melt. All right, so that means that you can only do so much in a limited area. And given that you can't increase the clock frequency, but you can still pack more and more transistors in, how can you actually stay in your power budget if you keep adding transistors? The only way to do it, or the only way anybody knows how to do it currently, is to specialize. You need more special purpose hardware that does one thing very efficiently, meaning at much lower power than if you didn't specialize it. So rather than building general purpose CPUs that do everything kind of okay, you start building things like GPUs that are very focused, say, on floating point performance for graphics, okay? And you have lots of other specialized computational devices that are focused on a class of computations and do those using much less power than the previous general purpose systems, okay? And this is a good strategy when you are limited by overall power consumption, okay? And really it's the only strategy. But what that means is that these machines become much more complicated. They become much more heterogeneous and non-uniform, as I kind of indicated in the discussion before, and they become much harder to program. all right? Okay, so the point of all this is that in the current regime, fundamentally you're power limited, all right? And that means you're going to have more specialization in order to make as much use of your power budget as you can. That means more complicated machines. And ultimately, you're also programming limited. You only have so many programmers who understand how to actually make any of this stuff work, how to write programs to any of it, and to train somebody to program all this stuff is really hard. All right, but as I said before, by investing in better languages and tools, you can actually produce systems that then allow many programs to be written that will take advantage of this hardware. So the highest leverage point has become to invest in new languages and tools that only a few people, a few experts have to write, but then many, many programmers can use them. All right, and this helps to manage and contain the complexity, but also means that you need a lot of improvements in that whole software stack of translations that I had before, because all those translation stacks, which the Java one I showed you, but there are many others, those were all designed in an era and built in an era when CPUs were getting faster every single year, okay, by a lot. And so they weren't really intended for this world where you have these very complicated heterogeneous machines. All right. So that's the kind of overview of why things have changed and why people are actually interested. And I think let's see if I can get my talk back up here. Yes. And so now I thought what I would do is just spend a few minutes, talking about a few specific research problems. There are many others. Again, and full disclosure, these are the ones that I've been working on, so I happen to know a little bit about them. But it's by no means the full picture of things that that need to be done or that could be done to help bridge the gap between the complicated machines people are building and the kind of programmability that we need in order to make these systems actually work in practice and be sustainable. So here was the Java stack, and the stuff from x86 on down, that's somebody else's problem, that's Intel's problem, so I won't look at that. But we could talk about some different pieces that might go in higher levels of the stack. One is domain-specific languages. I'll spend a few minutes talking about those. And then a little bit about DSL infrastructure. So how do you, if you're interested in domain-specific languages, how do you actually build a lot of them, okay, and the problems there. And then I'll talk a little bit about memory and data movement in particular, okay, and some of the new issues that arise in implementing and designing programming systems for the reality that you have these very complicated memory systems in modern machines. All right, so DSLs. So here's a picture that I really like. Whenever you write a programming language, you want to have some combination of performance, productivity, and generality. So generality is what kinds of programs you can write. Productivity means how easy it is for the programmer to write those. And then performance, of course, is the quality or the speed of the resulting code. And in general, in programming language design, it's easy to get 2 out of 3 of these. Okay, nobody ever gets 3 out of 3. And that's why you have lots of different kinds of programming languages, because people are optimizing for a different 2 out of the 3. And on the left-hand side are the domain-specific languages. These are the languages where you want performance and productivity, but you're willing to sacrifice some generality. So you're not going to write any kind of program. You're not going to write. You're going to give up on being able to write every program in the world in exchange for having, in some specific domain, having the ability to write programs that run really well and are relatively productive in a productive system for the programmer. So the programmers can write the programs easily and they perform reasonably well. And things like SQL, R, MATLAB, RenderMan, these are the kinds of languages. Each one has its target domain and has abstractions specifically for that domain. So by being domain specific, we can get productivity and performance. So essentially, this is a smarter compiler that, in addition to doing all the things that a compiler normally does, also knows something about the domain. It has some built-in knowledge about that domain and can carry out optimizations specifically for that domain. So let me give you one example. Of a mesh domain-specific language. So don't ignore the colors here for the moment and just focus on the underlying dots and edges. So a mesh is just a graph, okay? But in many, many domains, especially in science, there's a lot of computations that can be expressed as programs over meshes. And the basic idea here is that the domain-specific compiler for a mesh domain-specific language will have knowledge of a mesh. It'll know that it's operating on a graph, okay? And the interesting thing about mesh computations is that they tend to be very local. So everything is done from the point of view of operating on a particular point in that graph and then its neighbors. So typically you're talking about a neighborhood called the stencil around a specific point. You might do some computation. So for example, you might have a graph. Every node in the graph has a temperature, and the computation might be to take the average, to update the temperature at every point at each step will be the update, will be the average of the temperature of its neighbors. So you have to get all the information from the neighbors, compute the average, and then update the value. And you're going to do this for every point in the mesh, all right? And the mesh is fixed for long periods of time so that you can actually do things with that mesh inside a compiler, and you'll then get that, with the time you spent on that, you'll get back over a very, very long running computation. And in particular, one thing you might want to do is partition the mesh for parallel computing. So in this case, you might want to break the mesh up into 3 pieces, okay, and spread them out, say, to 3 different processors. But then because there's always a neighborhood, a stencil, some neighborhood around each point that you need to gather data from, there'll be some points on the boundary, and that's what the colors in the middle indicate. So the points in the middle are the ones that are shared between different pieces of the mesh because, multiple, even though the mesh is split up 3 ways, some pieces of the mesh will need to go and get information from other pieces of the mesh for those points on the boundary, all right? But in a domain-specific compiler, you can stare at the mesh, you can figure out a good way to break it up, you can spread the pieces out to different parts of the machine, and you can do all of that automatically, and then carry out the mesh computations in parallel. All right. So now one key thing in a language design for something like this is how you describe the mesh. So how does the programmer tell the compiler what the mesh looks like or what the operation is it's going to perform? And traditionally, people would write it like this. Okay, they'd use an array, they'd encode the graph in an array, and then they'd have indexing arithmetic to indicate, what piece of the array you were referring to when you were going, to get, say, the neighbor of a particular element of the graph. And this is really awful. All right, it's hard for people to read, and actually compilers don't understand it either. All right, analyzing all this index arithmetic, you're encoding the graph in a very low-level way, and so this is not a good domain-specific representation. What you really want is something more like this, okay, where you actually have topological concepts in the language. So, if you have a mesh, you might as well have a concept called an edge, okay, and a vertex and things like that. And you might say, well, if I want to do a computation on a vertex and I want to get its neighbor, well, then every vertex has a list of neighbors. And so I can just say, vertex.neighbor, give me the first neighbor, give me the second neighbor, whatever it is. And then this will be something that both programmers and the compilers will understand better. All right, and so by actually avoiding this kind of low-level encoding and actually having concepts of a mesh directly reflected in the language, you can do a much better job of compilation. And so at Stanford, we built a domain-specific language called Lisp, which looks like this. And just point out a couple of, I'm not going to explain any of this stuff, but it's not very hard to read. Here's a little function that works on edges, and it gets the vertex at both the head and the tail of the edge. So every edge, of course, has 2 nodes on either side of it, 2 vertices on both the head and both ends of the edge. And then there are various properties associated with the edges and with the vertices, and you can read those off like temperature and position and do some calculation and update the values on the vertices and edges. And the important thing from the language design point of view is, first of all, from this description, it's very easy to figure out what the stencil is. Okay, so given that I know that I'm reading a particular edge, E, then I can see that, well, what am I going to fetch from E? I'm going to fetch the head and the tail, so the 2 vertices attached to it. I'm going to fetch various properties. I can read all that off from this particular function, all right? And so I can, for every edge, I can actually statically infer exactly what data it's going to access when it runs this function. And the other important property is that this has a sequential semantics. So there's no parallelism here, there's no discussion of complicated hardware. All of that's going to be taken care of by the domain-specific language. So I'm writing at a familiar level of abstraction here for most programmers, and I will take it, I'll use the domain-specific knowledge about the fact that this is a mesh computation to manage all the complexity of programming the machine that I need to make this run on. Okay. The interesting part of this is actually what you do with loops. And I didn't, I'm going to deliberately skip over that because I'm trying to keep this at a very high level. Essentially loops are implicitly over every edge in the mesh, so I'm going to write a computation for each edge, and then I'm going to say, do this for every edge in the mesh. And there have to be some restrictions on that to guarantee that this makes sense when you execute it in parallel and you get a deterministic result. Okay, but that's not very hard to do, and I think the restrictions that you get are fairly natural for programmers to understand. Okay, and the result is that you get both productivity and performance. I mean, this actually works out to work, to work really well. Okay, so let me touch on the next topic, which is Dsl infrastructure. So yeah, that was one domain-specific language for one very particular domain, and there are probably hundreds of domains for which you might like to build an infrastructure like this. Okay, and in a big system, you're probably going to have more than one of these in the future. If DSLs actually become very popular and people develop many more of them, you're going to need these to work together in realistic systems. And also, writing a compiler is still a lot of work. So how are you going to lower the cost if we really need all of these, all this specialized knowledge built into our tools? How are we going to actually make that happen and make it feasible to write all of these domain-specific languages? So this is another issue that I've been thinking about, so you need some kind of common basis for code, data, and program transformations that could support many different domain-specific languages, and you need to be able to generate efficient code. So you need to be able to, you need some target that actually allows you to get at the underlying efficient constructs in the hardware. And so a system we've been building is called Lua Terra, is a first cut at this, and I don't mean to say that this is the solution, but it's an interesting design point, and we've been using it for quite a few of our own projects. It's really two languages that are built into a single overall system, okay? So one is a high-level dynamic scripting language, and we chose Lua. And that's because it's well known in the graphics community and interoperates really well with low-level languages like C. And so but basically Lua is like Python or any other scripting language that you're familiar with. It's untyped, it's garbage collected, it's designed to be very productive but not very efficient. Okay? And so here's a little function written in Lua that adds two numbers, and if you call it with 3 and 4, it prints out 7. And then the second language is called Terra, and it's a typed language just like C. Okay, it has a syntax similar to Lua, but essentially it's C. Now you have to declare the type of everything that you work on. So you have explicit types, and the functions are all compiled. So there's an optimizing compiler that will take Terra functions and emit good low-level machine code. And so in this case, here's the same function written in Terra. All right. Okay, and then how do you use these two things? I mean, what's the advantage of having access to the two languages? Well, obviously you can use the low-level language to generate efficient code. You're not going to get really efficient code out of the high-level language. But the low-level one will give you, if you want a particular function that's going to be very, very fast, that's a good way to do it. But the real advantage is to use the high-level language to generate the low-level language and do this through metaprogramming. So this is an idea that goes back to Lisp. Basically, you have macros. And so here's a little function that returns the square, but it doesn't actually just compute this. It doesn't just compute x times x. What it does is it produces code for x times x. Okay, so if I call gen square, then what it's going to do is it's going to give me back the expression substituted in for x. So if I call gen square on A, it's going to give me back A times A. And if I call gen square on B, it's going to give me back B times B. All right? And so I can write little pieces of code in Lua that will return fragments of optimized code in Terra, and I can even do program transformations on them. Basically, I can use macros, macro-like facility. It's not exactly macros. It's what's today called metaprogramming, to do all the kind of manipulation of program representations that a compiler needs to do, and I can do this within the language. So here's a little example. You have the Lua function up there, and then down here you have a Terra function, and instead of writing out explicitly what this function is going to do, I'm going to use metaprogramming, so I'm calling the Lua function, which will produce the code that I'm going to splice in between those brackets. All right? And so when I do that, what I get back then is a Terra function that computes A times A and B plus B times B. All right? And so in this way, you can program a compiler using the convenient high-level language, but at the same time use it to produce the efficient low-level code. All right, and these two languages are designed to interoperate together. They live in one environment, and everything is designed to mesh nicely. Okay, so I think I covered all of this stuff. The main thing about the Terra Lua system is that the two languages, on a technical level, they have a similar syntax, but most importantly, they have a shared lexical scope. So variable names from one can be in scope in the other. And then the state is shared through a JIT compiler on the Lua side. All right, and then the last topic that I'll just touch on is dealing with complex memory hierarchies, because this is really a new feature. I think that's become, well, it's not really a new feature, but it's become a much more important feature of the way machines are built in the last decade. So people put a tremendous amount of thought into how to take advantage of modern hardware for parallel programming, and there's lots and lots of ways to parallelize code, basically to do two things in parallel. But there's been much less attention paid actually to how you deal with your data. And actually in these machines, it's not the compute that's usually the dominating cost. And more, it's actually the movement of the data that dominates the performance of programs. All right, and that's because, as I said earlier, data movement speeds are improving less quickly than processing speeds. So here's a little classical piece of code if you're just going to write a dot product. And the thing just to notice about this is the way almost all languages look. But there's nothing in here about where the data comes from. Okay, so it tells you what to do and in what order to do the operations, but it doesn't say anything about where the data lives, where it has to get moved to. All of that is hidden and somehow managed by magic in the language implementation. And compilers have particular strategies for doing that, but programmers have no control. Okay, there's no programmer option anywhere to say, I want this piece of data to live here in the machine or someplace else. And that's a real problem. It'd be when memory movement becomes a first-class issue for getting the performance you need out of programs. So here's just a simple use of that dot product program. I'm going to create two vectors, and then call the function on them. And the typical evaluation for this would be, well, after the dot product has been called, then I'll move all the data to where the computation is being performed. So first I compute first I create the first vector, then I create the second vector, then I start running the dot product, and as I refer to elements of it, I go and find them and bring them in and do the calculations. But that's actually a terrible strategy on most machines today. All right, usually it would be much, much better to do the following thing. First, you would create the first vector, then you would create the second vector, and then you would move those vectors to where you want them to be to perform the computation before you even start running the dot product. Okay, so you would actually do the data movement first, get all the data in the right place, then call the dot product function. And the reason that's better is because it would allow you to do some other useful computation while you're moving the data. So you can move the data through the data pipeline of the machine. That doesn't involve your CPU, and you could be doing some other computation on the CPU and get parallelism between the memory movement and the computation. All right? And so, so we've been looking at a system for doing that. Okay? And so instead of writing programs that look like this that don't talk about data movement, okay, and this is a kind of a graph representation of the program, all right, with the dependencies. So first I create A and I create B, and it doesn't matter what order I do those in, and then once both of those are done, I can do the dot product. you'd really like to be able to express the order of operations like this, create A, then move A to the right place, separately create B, move B to the right place, and then do the operation. All right, so I'm running out of time here, but I'll just very quickly mention that we started to develop a language around this idea where you explicitly name the parts of the data that you're interested in. Okay, so you have things called regions, which name sets of data, and they look a lot like arrays. But when you name a region, you're really talking about the whole thing. It's not just a pointer to the array; it's actually the whole block of data or a set of data that you're interested in. And so then tasks that work on regions and explicit data movement operations that make it at least clear to the compiler where data movement needs to happen. And then in these regions, what can you do with them? Well, once you start having regions and you're talking about sets of data, then you need to be able to do various kinds of things with them. You need to be able to partition them into subregions. And one thing we allow is to have multiple partitions, and also that partitions don't need to be disjoint. So actually you can divide into subsets that overlap and have aliasing. And so then you get these things we call region trees. So you have some set of data that you're interested in. You can partition it up into smaller pieces of data. And you can also, so a partition is represented by that horizontal bar, I should say. And then in some cases where it gets really interesting is when you want to have multiple partitions of the same data set at the same time. All right, and then I'll just give, there's one computation that we've done which is a realistic one, does chemical combustion. And I'll just mention some performance results very quickly. So, so the bottom line there is the standard implementation using conventional tools. The top one is the one where we can talk about the data movement in this way and actually get more overlap between the data movement and the computation. And you can see that we're 3 times faster even on small numbers of nodes. The vertical axis there, the horizontal axis is roughly how many processors this is running on. But then as you move out, it scales even better. So by the time you're up to very, very large numbers of processors, the ability to do a better job of data movement results in even bigger performance gap between the standard way of doing this and this way that's that actually allows the programmer and the compiler to have more control over where the data lives. So to summarize, I think the world has changed. Exploiting future hardware is going to require new tools. It's not just a nice thing to have, it's actually going to be necessary, both to exploit performance and just to maintain acceptable productivity. If we even want to maintain, because the machines are getting more complicated, if we even want to maintain the level of productivity we have today, we need more expressive tools. And so there's a resurgence of interest in this area as a result. And here's a few links, and I should stop. Thank you very much.